Hello and welcome to the next lesson, lesson 5.3, graphing polynomials. But not just graphing them, just kind of looking at the graphs of polynomials, understanding their characteristics, understanding how to make a graph from an equation, or possibly be able to maybe piece together an equation based off a graph, just things like that, yeah? Now I will say, I'm a little sad because I think this lesson is much better taught in person than virtually online, just because I get to really play with Desmos and point and observe and just make gestures and stuff, which I can't do on this online medium. So just know I might be making gestures and you just can't see them, okay? Maybe I'll draw little doodles. I'll say, hey, look, it's Mr. Spake. He has a big tummy. There's Mr. Spake. And he's making gestures, and he's waving, right? And he's got all this energy above him. Okay. So lesson 5.3, we're going to talk about first what's called multiplicity of roots. So if you remember from the first lesson, also I'm tired of red. All the notes were in red last. We're switching to blue. R is said to be a root of a polynomial f of x if what? And this is something I would post to the class online. And I would say if, and then I would pause, and then the classroom would say f of r equals 0, hopefully. But usually it's just one or two students, right? Ideally, it would be the entire class, all 32 of them, shouting to the sky, f of r is 0, right? But whatever. So this is a definition from the last unit, right? This is what it means to be a root. When you take a root and plug it into a function, it evaluates to 0. Do not forget that. Moreover, if r is a root of f of x, then that means x minus r is a factor of f of x, okay? So if you knew that r was a root, then that means x minus r is a factor. Specifically, a linear factor. So just, keep that in mind. Now, this next piece, if you just read it by yourself, it might sound a little confusing, but I assure you it's not that bad. It says, let p of x and q of x be polynomials such that q divides p. All that means is q is a factor of p, yeah? Then we would say that if, assuming p of x has roots, which it should, r is a root of multiplicity k of that polynomial p of x if p of x equals x minus r to the power of k times q of x. You say, huh? What? Look, this is just all the other factors. We don't care about her, yeah? We care about him, king. We say x minus r to the k, yeah? K is for king. Q is for queen. Look at that. Okay. I gotta have fun with these videos somehow, right? So anyway, you don't really care about this. You're focused on this factor here, right? X minus r is the factor where r is the root. K is called the multiplicity because it's the number of times the root occurs. So if k is 1, then r is called a simple root. This is most of the roots you've encountered so far, but you've encountered other kinds of roots. In particular, you've counted double roots with parabolas. So if k is 2 or more, then r is called a multiple root. So multiple. You could also say repeated, okay? So you could say a multiple or a repeated root. Now, the multiplicity, this is important vocabulary. You know what? I'm putting it in gold. I'm underlining it. I'm starring it. That's what I'm doing. The multiplicity of a root is the number of times it occurs, okay? So let me illustrate that with this example here. So it says the polynomial f of x, blah, 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 can be factored like this. So you see two roots, right? Right here, I have a negative 4 as the root of x plus 4, and I have 1 as a root of x minus 1 squared. But you notice x minus 1 squared means x minus 1 times itself, right? So that root 1 is happening twice. And that is what is meant by multiplicity. Yeah? Multiplicity means the number of times that root is happening. And we know that 1 has a multiplicity of 2 because it occurs 2 times. But you don't need to write it to see that. You just look at the exponent. And that's what's meant by that k there. Yeah? That's it. Okay. So what goes in the blank here, basically, is you'll notice that x plus 4 is to the power of 1. So you have a simple root, because k is 1 at negative 4. So simple root, sorry. A simple root at negative 4, because k is 1. On the other one, k is 2. So we could call this a root of multiplicity 2. So you have to specify how many times it occurs if it's not a simple root. Yeah? Specify, it's a root happening twice. We call that root of multiplicity 2, which is occurring at 1. Alternatively, you could call this a double root because it's happening twice. And at this point, I would say, class, if a double root is a root of multiplicity 2, then what's a root of multiplicity 3 called? And then you would say with confidence, triple. And then I would give you a thumbs up. That's a thumb. Here's me with my thumbs up. Okay. And now we go to characteristics of polynomials. And this is, again, why I prefer this in person, because I get to call and respond to. I get to say, hey, class, what do you think about this? And then we explore things together. But now I'm just talking to a rectangle in my hand. Anyway, here's some important vocabulary to know. I would star and know all of it. I would just say, all of this goes in my brain. It's a terrible brain. Let's draw a little bit of in the stem. There's my brain. All of this goes into your brain. All right? Every single one of it. Every single that you memorize, every single thing that's on this little page right here. Yeah? The first few parts are pretty easy. The first thing is vocabulary. Oh my gosh, I can't speak. The first thing is vocabulary about local maximums and global maximums, as well as minimums, okay? Local means within a sort of specific region. So it's, and then global means everywhere, right? Just think what the words mean, right? Global enterprise would be all over Earth, right? A local organization would only be in your hometown, right? So global refers to the entire domain, right? If you look at the function for its entire domain, that's global. Local means you're just looking at within a specific interval, right? Between these two values, right? So that's what local means. So when you say a local max, we actually see a local max on this graph here. Right here, you'll notice that the graph is sort of going up and then it turns. It's a turning point, goes back down. This is a local maximum. It is not the absolute maximum. It's not the highest point on the graph because these arrows imply it keeps going up, right? In fact, if it keeps on going up, both on the left and the right, there's not going to be a highest point. There's actually no global maximum. That's because it just keeps on going, right? But we do have a local max, and that's important. You kind of see the difference there. The next is minimums. You'll see that down here, you have the lowest point of the function. This would be the global minimum. But we also have a local minimum at 2 right here because it kind of comes down and then goes back up. So it's the lowest point. You know, if you were to sort of just look between here and here, that's the smallest value, right? So this is called a local minimum. Minimum. Okay. And that's that. Okay, that's pretty straightforward, I think. The next piece is on the behavior around roots, which, I use the word root a lot. I should also say zero in my vocabulary because you're going to see that one too. Roots and zeros, same thing. Yeah, they mean the same thing. So, depending on the root's multiplicity, the graph will behave differently around that root. Maybe the best way to describe it is that a root will behave, the root's multiplicity, if you think about a parent function to that power, it's going to behave like that around the root. You say, huh? What? And I say, let's go to Desmos, okay? This is the best way I can illustrate this. So suppose I have two roots. Here's x plus 2 and x minus 2, x plus 3. You know what? I like 1 better. There it is. So you can see I have two linear factors, and they just kind of pass through, right? So at both roots here and here, they just pass through the x-axis. But suppose I make the root at -1, which is right here. Suppose I make that multiplicity 2. So what that means is I'm going to raise this to the exponent of 2. And so now you'll notice, the graph has changed quite a bit. At 2, it's still just doing that passing through motion, right? It's just kind of, I'm going right through. But if you look at -1 now, which is the root with multiplicity 2, it doesn't pass through. It sort of bounces. And I wish I could sort of draw here, but I'll try to move the cursor. See, I come up, 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 and then I bounce off this, right? And so that's what happens with multiplicity 2. And if you think about it, and this is the part where I wish I was in class, I could really show you, but zoom in. Let's try to zoom in here. Just around that region, what's that look like? And you would say, a parabola, Mr. Spake. And I would say, yes, class, yes, that's a parabola. You see, the multiplicity is 2, so it's behaving like a quadratic in that region, right? And there you go. Now, do you remember what a cubic function looks like? So as a reminder, because we just got back, we just finished parabolas, but it's been a minute since you've seen x cubed. Here's a reminder. X cubed looks like this. We talked about this in Unit 1 with all the parent functions. Here's the cubic parent function, right? This middle point here is called an inflection point because the graph changes curvature. It changes what's called concavity. To the left of this point down here, the graph is sort of scooped downwards. We call that concave down. Up here, the graph is scooped upwards. We call that concave up. So when a graph changes concavity, that's called an inflection point. Anyway, all that to say, look at this shape. You see how it kind of wiggles through the origin right there? So I'm going to go back to our graph, and instead of being -1, instead of having multiplicity 2, let's change it to multiplicity 3. Aha! Observe, right? It looks cubic in that region, right? Around that point, this root has multiplicity 3, so it's kind of acting like a cubic there. Thing is, this is not a cubic polynomial. Eventually it changes, right? I mean, there's all sorts of other stuff going on here, but around the root, right? Around there, it's acting like the multiplicity 3. And so you can experiment with all sorts of stuff. Notice if I put a 2 on x minus 2, so that cubic sort of behavior, right? It's an inflection point at this root. We call that a triple root. But then it comes up, and down here, rather than passing through, it just bounces off. Yeah? And so these are just things to observe. If I put another one, let's say at x, then notice you can see all three. It's wiggling through this. It's passing through the linear term. And if you think about it, if you really zoom in on this, You see how that's more or less a straight line? I mean, it's not straight, but it's behaving closer to a linear function than anything else around that root, right? Whereas this one's behaving like a parabola, and this one's behaving like a cubic, right? And this goes for all the other functions. But when you change it with even multiplicity, so you'll see that right now it's 3, change it to 4, I still get a bouncing motion. So when it's 4, it still bounces off. When it's 6, it bounces off. When it's 8, it bounces off. When it's 10, it bounces off, right? So as long as the power is even, if the multiplicity is even, the function will go down or it'll go up, and then it'll return the same direction, okay? If you mess with odd powers, if it's a power of 3, it's an inflection point wiggling through there. Power of 5, same thing. Power of 7, same thing. I mean, it's getting wider and, it's growing slower, faster, right? But it's still that sort of, it's a similar curvature, right? So it does that sort of wiggle motion. So anyway, that is all to explain the information that is given right here, okay? So the idea was, if you look at our graph here, get this off my keyboard, right here at -1, that's a simple root. Right here where the local minimum is, that's a double root, because you see how it's sort of quadratic in this region, right? Whereas this is kind of like linear, and this one's kind of like cubic, right? This one is a triple root. And you can tell this by the multiplicities. So if it's multiplicity 1, simple root, even multiplicity bounces, odd multiplicity creates inflection points. Okay? All right. Now, the last thing to talk about, and I'm going to go back to Desmos here, is end behavior. So end behavior describes what's the graph doing on the left and right ends. So if I zoom in here, right, as I go to the right, where is the function going? Or in other words, as x travels to the right, where does y go, right? Does it go up? Does it go down? Does it approach a value? Does it stop somewhere, right? Well, you'll notice as this function goes to the right, it's also going up. So the way I would say this is, as x goes to the right, which is to say as x goes to infinity, the function, which is the y values, goes to infinity because it goes up and up and up and up and up and up and up, right? On the other end over here, as x goes to negative infinity, so I say as x goes to negative infinity, the function is still going up and up and up, so f of x goes to positive infinity still, right? And that's what's meant by end behavior. Now, the rules are here to know and memorize, but they're easier to memorize when you play around with these things, yeah? Just memorizing just because I told you so isn't going to help. Play around with it. Go into Desmos and just make up stuff. You'll start to see patterns between the polynomials. And so I'm going to do that just for a couple minutes here. Well, I hope it's only 2 minutes, but who knows? It could take an hour just talking about these things. I'm going to make x to the 4th minus x cubed minus x squared plus x. Okay? And so I've just made this polynomial. And so I want you to pay attention to two things. The first is the degree. You'll notice that the degree of this polynomial, I set it to be 4 because 4 is the highest exponent, right? Of course, I could change it to 5, right? And I want you to, as I change the degree, observe what happens to the end behavior. So as you can see, it's kind of like the one we were just talking about. As I go to the right, it goes up. As I go to the left, it goes up, right? Now, I'm going to change the degree from 4 to 5. And now notice how the end behavior has changed, right? With 4, the right side was going up. With 5, the right side is going up. But with 4, the left side was going up. With 5, the left side was going down. Now make it 6. Oh, they're both pointing up. Now make it 7. Oh, the right side's going up and the left side's going down. Now make it 8. Oh, they're both going up. Now make it 9. Oh, one side's going up, one goes down. Now make it 10. Okay, you see the pattern, right? Even degree means the end behavior is the same, right? It's going to go either both up or both down, although we haven't seen an example of both down yet, right? But the idea is the end behavior is the same when the degree is even. If the degree is odd, however, then the end behavior is opposite. It's not just different, it's the exact opposite. As I go to the right, this one goes up, but as I go to the left, rather than going up, it goes down, right? So just know if it's odd degree, they point at different ends. Now, might ask, go back to my 4 here. These are both pointing up. What do you think would make them point down? And so this is a moment in class where students offer suggestions verbally. They shout things out. And hopefully, usually, someone says, make it negative. And you might say, well, what do you mean by that? Right? What do you mean make it negative? Make what negative? Change the sign on one of the variables? Who? Right? What? If you remember function transformations, right? Like if I had x squared, hello? It's not, what's going on? It won't type. Hello? It's not typing. Okay, whatever. I guess I'll just do this. If this was x squared, right? Then if I put a negative, I still can't type. I'd have a negative and it would flip it down, right? Okay, the delete key works. Interesting. Okay. So the idea is if you make the leading coefficient negative, then it flips it upside down, right? That's a vertical reflection. Although, careful here, it's not a 100% vertical reflection, right? I mean, that's not the same shape upside down, right? It became a totally different shape. If I make the whole thing negative, then that flips it. That's the whole thing. But that's not what I'm focused on. I'm just focused on the lead coefficient. If the lead coefficient is negative, then it goes down, right? Now change this back to 5, right? So you'll notice the left side goes up and the right side goes down when it's negative. If it's positive, that's inverted, right? You see the difference. Woo. Okay. Anyway, the premise is if the leading coefficient is positive, as it goes to the right, it'll go up. And if it's negative, as it goes to the right, it'll go down. And so you'll just sort of put those two pieces together. Pay attention to two things, the degree and the leading coefficient, okay? That is what determines your polynomials and behavior. Let's do some problems. Yeah, let's analyze some of these, okay? So practice analyzing polynomial graphs. So it says, given each function, describe all key features, including the global minima and maxima. By the way, that's plural of minimum. Each root and their multiplicity and the function's end behavior. So I have the equation given as well as the graph, just baby steps here, right? You can see, correlate the equation with the graph, right? I have a root at 0 with multiplicity 2 means the root at 0 bounces, right? I have a root at 3 that's a simple root, so it passes through. And I have a root at -2. It's a simple root. It passes through. And because it's negative, as it goes to the right, it goes down. Okay? And that's because of that negative piece there. So to analyze this, which I basically just did, but it's fine. We're going to analyze it all the way through. You have 3 roots here, here, and here. One of them has multiplicity 2. The degree of the polynomial is determined by the highest exponent in your polynomial, right? And often, sometimes when I say this, a few students will say, Oh, it's 2, because 2 is the highest degree. Except, well, yeah, the highest degree of the factors is 2. But these are all factors of some larger polynomial, right? The degree of that term is 2, but not the whole thing. This is 2, this is 1, this is 1. Put that together, it's 4. So the degree of the polynomial is 4, because when you multiply all this stuff out, which I'm not going to do, but if you multiply, you distribute these, and then you distribute all that together, you will get x to the 4th as your leading coefficient. Again, I've got some roots. I've got simple roots at -2 and 3. And I know this, again, because of the behavior here, as well as the multiplicity up here, right? And then I have a double root, or you could say a root of multiplicity 2 at 0, because it's bouncing off right there. And x squared tells you it's double root. Minima and maxima, so this is, you don't need to find the points. This is the global max because it is the highest point. This is a local max because while it's not the highest point, it is locally the highest within a specific region. This sort of trough down here shows me a local min. And because the arrows point down, there is no global minimum. Right? You'll see, oh, right, it goes down and down and down forever. There will be no global minimum. And then lastly, the end behavior. As it goes to the right, it goes down. As it goes to the left, it goes down. So the way you write that is you say as x goes to infinity, f of x goes down, which is to say negative infinity. As x goes to the left, which is towards negative infinity, f of x also goes down, negative infinity. And so you can see that this end behavior is the same since the degree of the function is even. Also, the coefficient was negative, which means it faced down. Okay. And that's all we're doing. We're just practicing. This is just class practice. You know, it just takes time. If you think you've got the lesson, I mean, hey, move on, right? Move on to, what the heck else is in this? Oh, that and that. Oh, that's going to take me some time. Okay, here we go. You say, don't misinterpret that. Look, it's 9:18 p.m. And when I got home, I ate some Parmesan chicken, and I watched the first episode of Invincible. Is that how you spell it? Wait, it's not a C, right? It's an S. Anyway, wait. Is that a C? Invincible? Okay, I'm bothered. I can't do this. Hold on. I have to look this up. It's a C, right? Okay, thank goodness. It did not look right with an S. Okay. Anyway, I started the first episode of Invincible. And not of the second season, mind you. Okay, I've been caught up. But there's 3 other episodes to watch. And it's 9:19. And I want to go back and watch some more. So that's why I was sighing. Okay. Let's get through this. So I've got, you'll notice a triple root because it says x minus 1 cubed means my root is 1, and you can see that cubic motion there. It's an inflection point, right? So it's inflecting about that point. So I could say a triple root at 1. I also see a double root at -2 because of that bouncing motion, right? Double root at -2. By the way, you really, from the graph, you really can only safely assume it's an odd multiplicity. Do you really know that it's degree 3? Maybe, but it could have been degree 5, and this could have been degree 4, right? Like, you don't know. The bouncing motion is characterized by even. What really tells us that it's double and triple are the multiplicities given by the equation, right? Okay. You'll notice the degree of the polynomial I have a 3 here and a 2 here, so that's going to be an x cubed. Once this is all expanded, you get an x cubed. Once all of this is expanded, you get an x squared, and you're going to multiply those to get x to the 5th. And so the degree of the polynomial is 5. Minima and maxima, well, that is a local max, right? Because within a specific region, it's the highest point. This point is a local minimum, and that's it. There are no other ones. They're just those two. Local min. Okay? And notice, no global max, and that's because this graph points up forever, right? But there's also no global minimum because this graph points downwards forever. Odd degree polynomials will never have global max or mins. That's interesting. As n behavior, as I go to the right, it goes up. As I go to the left, it goes down. So the way I describe that is as x goes to positive infinity, f of x goes up, which means it goes to positive infinity. As x goes left, which is negative infinity, f of x goes down, which is negative infinity. Done. Okay, and so that's just practice analyzing. Okay, let's talk about these. Now, what's interesting about these problems is you have to create the graph, and you must create the graph based off the equation and only the equation. So you say, Mr. Spake, how do I do this? Well, and by the way, these aren't going to be 100% accurate, and that's fine. You are really just analyzing what the general shape of this polynomial looks like, yeah? Where are the roots? How is it acting around the roots? And what is the end behavior? Those are the three things. In fact, I would write that down. I would tattoo it on your arm. Just kidding. You are children. You don't need tattoos. And you especially don't want to tattoo math right now, right? Your first tattoo would be like a pizza or something. So anyway, okay, Mrs. Bake, stop encouraging adolescents, minors to go get tattoos. I say, I'm not. I say, stop it. Where was I? So you care about those three things: end behavior, roots, and the behavior around roots. So we have a root at 3 because of this. We have a root at -3 because of that. And we have a root at 1 because of this. Yeah? So those are my 3 roots. I also care about the behavior around the roots, but I'm going to look at end behavior first. First, I need to figure out the degree of the polynomial. Well, the degree is, well, that there's a 2 there, and then a 1, and then a 1. If you multiply all that out, it's like x squared times x times x. That's 4 x's, which means the degree is 4. And the degree being 4 means the degree is even. And so because it's even, right, an even degree means the same end behavior. So I know that, right? I know that this function will either point up and up or down and down. But I have to figure out the next piece, right? So remember, I look at the degree, but I also look at the leading coefficient and whether it's positive or negative. Again, that fact is given down here, right? If the leading coefficient is positive, then as x goes to infinity, f of x goes to infinity. Meaning, if it's positive, it goes to the up. On the right side, it goes up. In this case, the leading coefficient is 1, positive 1, so the right side of the function will go up. I know this for sure. Yeah? And because it's even, the behavior on both ends will be the same. So up here, it'll also be pointing up. Now, our goal is to connect these ends through the roots, keeping in mind the multiplicity of the roots so we have that behavior modeled. Now, at one, it's a double root, and the other two are simple roots. So I'm going to start from the left here, and this is a little bit harder on an iPad, but I'm going to start from the left. Let's say I'm going to just be coming, it's coming down from here, right? So it's going to come down, and I've got to approach 1 somehow, so I'm going to have to at some point bend, right? And then it's going to come over to 1, but then it's going to bounce off, right? At 1, it's going to bounce off because it has even multiplicity at 2. So it bounces. And then it must sort of turn around again at some point. We don't know where that is, but it's going to turn around and then pass through the next root and then continue upwards. And that's the general gist of the graph. So there it is. Our roots, we have a double root at 1. I guess I don't really need to write this because blah, 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 but then I have simple roots at -3 and 3. Okay? And behavior, they both go up. So as x goes to the right, f of x goes to infinity. As x goes to the left, f of x goes up. That means positive infinity, like so. Okay. It does say label minima, maxima on sketch, but the thing is, you don't really know which one is which for sure. Typically, the further apart the roots, the higher that gap is going to be. So it's a pretty safe assumption to say that that's going to be global minimum and that's going to be local minimum. But I would be careful with that. It's not necessarily guaranteed. Yeah. It is guaranteed that this is a local max. That will be true 100%. We know that because it's going to bounce. That will be a local max. But whether this is global or local versus this one, you're not 100% sure unless you have calculus as a tool. Okay, but we're not taking calculus, so we're not finding those points. Okay, next example. Let's find the degree of this polynomial. There's a cube here, and then another, and then another. That makes 5. So the degree of this polynomial is 5. The roots, well, let's see. I have a root at -2. Well, x minus 2 means a root at 2. So I have simple roots at 2 as well as -4 because it's a power of 1 up here. So 2 simple roots at 2 and -4. And then this root, x cubed, this always gets students. What makes x cubed 0? 0. If you just see x and nothing plus or minus, that means the root is 0, right? So I have a triple root here at the origin on 0, okay? So triple root. Okay, at 0. Now let's analyze the end behavior. First of all, the degree is odd. So because the degree is odd degree means opposite end behavior. We saw that earlier, right? End behavior. Okay. So I just had to figure, okay, so if it points up to the right here, then this end will point down. If it's not that, though, then the right side will point down and this one will point. It's one or the other, right? The question is, which one is it? Well, look at the leading coefficient. The lead is negative. So as you go to the right, the function will go down. Yeah? It's kind of vertically reflected over there. So I know that it is going to come down over here. I'm going to erase this. It's going to come up from over here. Okay? And then we just got to connect these points. Yeah? And by the way, since we're there, as x goes to infinity, it's going to go down. So f of x is going to go to negative infinity. As you go to the left, which means as x approaches negative infinity, f of x approaches positive infinity as it goes up. Now let's connect these. So I'm going to kind of come down from this point here. We're going to pass through this point. We're going to kind of have to curve over here to this point. Now I'm going to really zoom in here. This is cubic, so it's going to be an inflection point here. So it's going to come up probably like that and then up like that, right? Because I don't think it's not going to be like that, right? Well, I suppose it could do... Which one is it going to do? Is it going to come up and through? Or is it going to come up and through? It's probably the first one. Yeah. So it's probably going to come up and through this, like so. Yeah? I think so. Up and through. So this piece of... I know I'm taking a while, but I want it to be kind of accurate. I'm just taking a guess here. It's going to come over, and then it's going to come up and through, and then it's going to back down like so. And so I kind of get that inflection around that region. I'm not sure that's it, actually. I think it's the other way. Let me check with a calculator, huh? Negative x cubed, x plus 4, x minus 2. Why don't we look? Let's see how accurate we were. Was my inflection good or bad? So it was negative x cubed, x plus 4, x plus 2, x plus 4, x minus 2. Okay, so the curvature, you can see, I'm gonna vertically dilate this some. That's too much. How about 8? Okay, so you can kind of see this is roughly what our picture looks like. It comes down and then it kind of scoots back upward, so it's going to go up and then inflect up. So it looks like the typical cubic. Is that what I have? Comes up and then inflects up. That is what I have, roughly. It just looks kind of goofy, doesn't it? Okay. Anyway, that's that. Looks pretty good. Also, I'm not, if I grade this at all, I'm not critiquing you on your squiggle. If it looks like a wiggle, you did it. Yeah? And be happy and proud. You're good. Okay? The function roughly looks like that. All right, let's move on. Because, like I said earlier, I want to go watch the second episode of Invincible. The fundamental theorem of algebra. So, the fundamental theorem of algebra. Oh my gosh. Do you know what fundamental means? Fundamental means important. Not really. Fundamental means like it's the foundation, right? This is the theorem underlining all of algebra. It's such an important theorem. It underlines everything about polynomials. It's also called the D'Alembert-Gauss theorem. Hey, look, it's Carl Friedrich Gauss. Here he is again. More so the first name, but that's fine. Gauss had something to do with it, right? Anyway, what it says, here's the official definition. It states that an nth degree univariate polynomial has exactly n many roots, including multiple and complex roots. Huh? Okay. Univariate means one variable. So x squared plus x plus 1. That's univariate. Only x is the variable. Multiple variables could like this, right? That's a multivariable polynomial, which we're not really working with right now, okay? What it says is that when you have polynomials with only one variable, which is what we're concerned with anyway, there are just as many roots as its degree. So the same number of roots as its degree, meaning if it's of degree 4, there are 4 roots. If it's of degree 5, there are 5 roots. And that includes multiple roots and complex roots. So example, you could have like x times x minus 1 squared. You know that the degree is 3. There's only, you'd say, oh, but there's only 2 roots, 0 and 1. But 1 happens twice because it's a double root. So there's technically 3 roots. Yeah? So fundamental of theorem of algebra includes multiple and complex roots. Okay? Now, here's group problem 1. And this is just a fun little thing I hand to you for you to explore in your groups. But I'm going to go through it in the video anyway. It says, below is the graph of f of x equals x to the 4th plus blah, 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 blah. Now, knowing what you just learned, the fundamental theorem of algebra, it says that the degree of the polynomial, whatever the degree is, it has the same number of roots. The degree of this polynomial is 4. So how many roots does f have? F has 4 roots because the degree of f equals 4. And this is because of the fundamental theorem of algebra. Thing is, how many roots do you see on the graph? 1, 2. I only see 2 roots. And based off the behavior around those roots, they look like simple roots. I have, let's see, 2 simple roots at -2 and 1. Now, so you ask yourself, okay, you see 2 simple roots and nothing else. But the fundamental theorem of algebra says that there should be 4 roots. So where are the other 2, right? This goes up and up forever. This is never going to come back down and get 4 other roots. That's not going to happen. So the question is, where is it? To have an authentic learning experience, I suggest pausing the video and trying this out for yourself, right? Discuss with your group how you could use the graph of this to find the other 2 roots. Because there are 2 more roots. It's just, what are they, right? But pause the video, take a stab at it. I'm going to go through the answer here. The way you solve this problem is using long division. So we talked about long division and synthetic division in the last video. So what you can do is this polynomial as it stands is not factorable. Notice it's 1, 2, 3, 4, 5 terms. Blech. Blech. That's probably not gonna factor well, right? So we can't really do factor by grouping. GCF, no. So how could we factor this? Well, if we use one of the known roots, we might get a polynomial that is factorable. So notice the one I just circled was -2. So let's use -2 with synthetic division. So if I go back to the poly, it's 1, 1, 2, 4, -8. 1, 1, 2, 4, -8, right? And I'm doing synthetic division. Go watch the last video if you're not sure what I'm doing here. I'm going to divide this polynomial by x plus 2. And I know that the remainder is going to be 0 because it's a root, right? So I drop the 1. 1 times -2 is -2. 1 plus -2 is -1. 1 times -2 is 2. 2 plus 2 is 4. 4 times -2 is -8. That becomes -4, and then that becomes +8, which sums to 0. Fantastic. So what you have here, if that's the remainder, that's the constant, that's x to the 1, that's x squared, that's x cubed, you have 1x cubed minus x squared plus 4x minus 4. Can you factor that? Can you factor this? Answer, yes. So try grouping, right? Here's x cubed minus x squared plus 4x minus 4. GCF of the first group is x squared, and this is x minus 1. GCF of the other term is 4, leaving behind x minus 1, which means this factors as x squared plus 4 and x minus 1. Aha. So, the full factor, and notice, x minus 1, that makes sense, because the other root we knew was 1, right? So I used one of the roots to create a polynomial that was factorable. I factored it, I found the other factors, right? And so now the f of x is fully factored, is x plus 2, x minus 1, and x squared plus 4. Now, those first two roots we already knew. We already knew negative 2 and 1. But what's new is x squared plus 4. Set this equal to 0. Solve for x to find the roots. Notice I'll subtract 4 from both sides. I got x squared as negative 4. To get x squared alone, to get x alone, you must take the square root of both sides. You're taking the square root of negative 4. Well, the square root of 4 is 2, but the square root of a negative we call I. Saha. There were two other roots, but they were complex, right? They were imaginary roots of this polynomial, which means we could not see them on the graph. So this is an instance where if you were to graph a polynomial, you might still be able to find the imaginary roots, even if it's not factorable, if you use long division. So what are the roots? Well, we found 1 and negative 2. Then we also found 2i and negative 2i. And this is nice and perfect because we wanted 4 roots, right? Also, remember, this is a note. Remember, complex roots come in conjugate pairs. And what does that mean, right? Well, oh my gosh, I don't like the way I wrote that E. There's the E. If A plus BI is a root, then A minus BI is the other root. So because 2i is one of the roots, then negative 2i is the other root. Yeah? They always come in conjugate pairs. Alrighty. Yay! I really like that problem. And I'm biased, I made that problem. I also made this problem. In fact, I make everything. I make pretty much all of these problems. Because I have so much fun doing it. Aren't these fun problems? Don't you just love this? I love it. Okay, group problem number 2. Your goal is to write a 4th degree polynomial in standard form that satisfies the following. And by the way, trying this on your own is quite a challenge. It's quite a task, but it's good. I encourage you to try this for yourself. If you are stuck, resume the video. But really, I want you to give an honest attempt on this because it's really an interesting problem. So, we need to write a 4th degree polynomial. So we need x to the power of 4. And it does say in standard form. So let's look at the information we're given. We're given a simple root at 2 minus I. And we're given a double root at negative 1. We're also given a point, which is the y-intercept. Now, notice part A says, it seems like you have only been given 3 out of the 4 roots. Right? Fundamental theorem of algebra says this 4th degree should have 4 roots. What's the last root? How do you know? Well, we know that since 2 minus I is a root, right? A root. Then what? Well, I mean, we just talked about it. Conjugate pairs. 2 plus I is the other root. Because, and this is the same thing we just wrote in gold, complex roots come in conjugate pairs. Oh my, I hate the J. Okay, conjugate pairs. Sorry, I feel like I took 7 years to write that sentence. Okay, so since 2 minus I is a root, 2 plus I is the other root. Now here's the thing. You have all 4 roots now. You could set up factored form. You say, what is factored form again? Well, f of x is some leading coefficient a times all your factors. X minus the first root, x minus the second root. That's what factored form was for quadratics. But we're not dealing with power of 2, we're dealing with a 4th degree polynomial, which has 4 roots. So that's my factored form function. And I don't know a, but I'll find a later. I do know that I have a root of multiplicity 2 at -1. So the root, right, this means the factor is x plus 1 squared, right? -1 is the root of that, and it's squared because of multiplicity 2. So in factored form, I can write a times x plus 1 squared. But then what are the other 2 roots? Well, it's x minus 2 minus I, right? This is going to be x minus 2 minus I. That will be the factor, because that's the simple, right? It's x minus r, right? X minus r. So you do x minus, what are you subtracting? 2 minus I. So that's the factor, right? And so that's what you're going to put down here. X minus 2 minus I, but you distribute the negative, you get -2 plus I. Repeat the same thing since you know the other conjugate root. You'll find that it's x minus 2 minus I. And if you're not sure where I got that, I encourage you to just think about it, okay? Now, you'll notice with the rest of the question, I know I'm moving all over the place. Multiply together any expression containing an imaginary term. The reason is, would we really write factored form this way? Not really. It's not typical to leave it like that. Yeah? Yeah, it tells you all the roots, but it has i's in it, and we really don't want i's with our polynomials. We're going to keep everything real if we can. So let's multiply this. Now, I've noticed what some students like is a box. And if you'd like to use a box, use a box. X minus 2 plus I. I have nothing against the box. Here's your box. Are you ready? What you're doing is distribution of 2 trinomials. This is x minus 2 minus I. X times x is x squared, then -2x, then xi, then -2x, then 4, then -2i, then -ix, then a positive 2i, and then -I squared, which is -1, so it's a positive 1. So you'll notice this and this cancel, this and this cancel, and so what I'm left with is this thing is x squared minus 4x plus 4 minus I squared. But that equals -1, so that's plus 1. So put that all together. Let's put it back in blue. a times x plus 1 squared times x squared minus 4x, and now it's plus 4 plus 1, which is plus 5. And so that's not a rectangle. That's our factored form equation. Now, we haven't found a, right? But finding a is the same way you've done in the past. We found a in the previous unit, right? How do you do that? Well, you have a point. You know you have a y-intercept at 0, -10. So the idea is y equals a times x plus 1, x squared minus 4x plus 5, where the point is 0, -10, means x is 0 and y is -10. So you do -10 for y, and then just plug in 0 for x. So 0 plus 1, 0 squared minus 4 times 0 plus 5. What you'll get here is -10 is a times 1 times 5. Or in other words, -10 equals 5a. This implies that a is -2. And there it is. You found a. Now for the tedious part. Now that you found the leading coefficient, multiply all of this out until you have standard form. So this is a mastery of distribution problem right here. F of x is a, which is -2, times x plus 1 squared, times x squared minus 4x plus 5. Now, you can distribute this however you like, all right? If you want to expand this and then distribute the -2, or if you just want to split this up into x plus 1 and x plus 1, and then distribute the -2 to this one, and then take that and multiply this, and then take that and then multiply all three of those, whatever floats your boat, yeah? Whatever you like. I'm going to do it the way I like. The first thing I'm going to do is expand x plus 1 squared to become x squared plus 2x plus 1. And I'm not drawing a box for that or anything. I'm just squaring that out, okay? And then here's x squared minus 4x plus 5. Let's go ahead and multiply those two trinomials. I will use a box for this one, okay? X squared minus 4x plus 5. And this is just to help you see all the distribution clearly, okay? Clearly. X squared times x squared is x to the 4th. Then this is -4x cubed, 5x squared. This is 2x cubed, -8x squared, 10x, x squared, -4x, 5. So these will combine, and these will combine, and these will combine, right? So what I'll end up here with is -2 times x to the 4th. 2x cubed minus 4x cubed is -2x cubed. X squared minus 8x squared is -7, plus 5 is -2x squared. And then -4 plus 10 is 6, so that's 6x plus 5. Okay? Now distribute the -2. And I'm just going to make sure I flip the signs on all these things that have negatives. Minus 12x minus 10. And there you have it, everybody. Look at that beauty. That's my function. Okay? So, yes, that was a lot. And yes, this is a test question. Now, I will admit, I don't think the test question is quite as tedious, okay? But all of these steps are part of it, yeah? This one was a lot because of the, you had a really complicated I distribution here, as well as multiplying two trinomials together. That's tedious. I know that, right? Nobody likes really doing that. I mean, unless you like distribution that much, more power to you. But yeah, just to let you know, as a heads up, this is a test question. I am going to be assessing if I give you roots and a point, just like I did it with quadratics, because it was on the last test too. But on the last test, it was just 2 roots and a point. Now it's 4 or 3 or 5 or whatever. It's, whatever it says on the exam. So keep that in mind. Know how to construct polynomials. I think there's a couple questions like this on the homework, and I hope this helps you out. So thanks for being here. It's almost 10 o'clock, and even though I'm a little sleepy, I think I'm going to go watch that episode now. I hope you have a good day, night, or morning, or whatever, and I'll catch you around.